Can you hear me? All right. Okay, so we want to continue today, and we do have a lot of flexibility actually. So now, so we are somehow where it's good. We are a little bit over half time, so let's think about where we stand, right? So we heard a bit, heard a little bit about basic theory of partial differential equations, starting with ordinary differential equations, and we focused on the evolution problem, okay? And we learned about basic concepts of evolution. We started to write some code, and this is one of the core things that we want you to do, start to write some code. I think all of you yesterday finished doing your ODEs and doing convergence tests and actually solving a related physical problem, even simple, which was this two-particle in spiral in the lowest order approximation emitting gravitational waves. So we could already do some physics and learn some interesting things. Now we have one thing that for certain we do, and what we need for next week, which is all of you have to code up, is wave equation with the method of lines. And we have to get that working until tomorrow. So some of the highest priority is to basically help you get that done. Okay, understand what's going on, and so some simple cases that we can study, illustrate a few of the concepts that we have learned a little bit more through examples, and at the end, actually as a Blackboard talk, I'll talk a little bit about boundary conditions, and I will write down the equations for the wave equation coupled to the Einstein equations in spherical symmetry, which is easy enough that once your wave equation code is working, you can code it up yourself, okay? And that would be a task for the next week, which you can achieve. The other thing, which I was planning to talk a little bit about tomorrow, and somehow it also depends on your input, which things you prefer to learn about, was to talk a little bit more, less technically, about the wider perspective. What other methods are available to solve partial differential equations? So for example, we are talking here about finite difference methods, which are very, very useful. There are other ones. There are spectral methods. There are finite element methods. There are finite volume methods, which is what David Nielsen is going to tell you about next week. There are things that they haven't talked about yet. If you have a solution for the Einstein equations, we want to understand the physics in this solution. We want to compute things like the gravitational wave signal. Okay, you solve the Einstein equations, you have the metric, but then how you get some physics out of that? Where is the black hole? Okay, where do I find this in the metric components? Where do I get the gravitational wave signal? So I was also trying to talk a little bit about these things tomorrow. This is kind of the rough plan. So the first, and then the other thing that I can do now, for example, is show you some little simulations, some movies of the wave equation in one space dimension, just to see what it actually looks like. And before this, maybe even just take the Blackboard and think a little bit about, for this problem that you're coding up right now, what do we expect to see if it works? What may happen if it doesn't work? Okay, but so before all of this, let's just take 5 minutes or so just to think about what are the problems that you have right now to code up the wave equation. What's the best way of helping you? Are there technical problems? There's a lot that you have to do, right? You have to. The basic mathematical algorithm is to evolve coupled. Let's just take them. Coupled ordinary differential equations. We talked about this before, right? So we've spent a lot of time. We have. Let's do it like that. If y dot equals f of time and y, and you coded all that up and it worked fine, and then we said, okay, let's now make y a vector, and that's also pretty fine, and we can think of this like, for example, y could be a simple coupled ODE, y1, y2, y3. It has 3 components. For example, in the first lecture we saw these Lorentz ODEs, which create this chaotic Lorentz attractor. These are 3 ODEs, 3 simple ODEs, so that would be such a system, right? But now we want to we have already taken a conceptually difficult step, okay, which is to say, well, actually this vector here, what it stands for is the different grid points which we have in the partial differential equation. So now we have different grid points here. Here we have grid point I plus 1, I minus 1, right? And this would be, let's say, maybe at t is equal to 0. Okay, and now so now the ordinary differential equation state vector which we evolve is just the values of the solution at these different points. For the wave equation, we have at least two components because we had, because of phi dot, sorry, we splitted that with in at least two variables, right? So we had pi dot equals phi comma xx and phi dot is equal to pi. So in addition, we have at each grid point we have two variables sitting. We have the phi sitting there and the pi. So for example, if you have n of these grid points, right, then how many equations do we have to solve? We have, in this case, 2 times n equations, 2 times n ordinary differential equations. So now on the level of the pure algorithm, this is simple because you can just forget now. If you just solve this ODE problem, you can forget about the interpretation that this is a partial differential equation, and you just solve this coupled system of ODEs, right? In the details, however, this may be a bit tricky because you have to make sure when you write your code, you have to make sure that your objects do have the right dimension. When you save your solution, now you're not saving a number at each time, but you have to save a whole array, which can create technical problems when you code that up in your programming language. You have to think about things as now when you save these things. Before we just computed the whole solution for all times and filled up the whole vector that corresponds to the solution. Now you have to you can do the same, but now it has a dimension more, or you just save these vectors phi I and pi I at every time. If you do that, a simple way would be at every time you write that into a new file. You calling these files, phi 1, phi 2, phi 3, and so on for the simple time steps. But then you have to think ahead a little bit already. Also, how do you want to plot that solution afterwards? For example, if you use GNU plot, you have to write the things in a certain way. You have to make new lines after each time step. You have to understand what's the file format that you need in order to plot your solution afterwards for the program that you're using. So you have to plan your output. What else? What else I want to say? You have more parameters, for example, in which you have to communicate to the different functions that you have coded up. So for example, when you compute your right-hand side, you have these different stencils, right? So for example, you have yours, what you would have in this case, you have, whatever, pi right-hand side, something like this, right-hand side. This would be phi, we have phi I plus 1, minus 2 phi I plus phi I minus 1, the whole thing divided by 2 delta x squared. So now you have to code this up. You have to think about you have to also have to communicate now a delta x to this function, which you didn't do before. So you have to add extra parameters, maybe other parameters. And you have to think about, well, we have a vector of a certain length that is boundary points. What do I do with the boundary points? Right? This is something we talked about it yesterday. So periodic boundary conditions means that we just have to get at the boundaries of the grid, You just have to get this value from the other side and this from the other side. In most of these programming languages, or many of the programming languages that you're using, you have vectors and matrices conveniently implemented, and often you would have if you have this, if an array phi, for example, you could just say you have a syntax like phi of index minus 1 would be just the last one on the other side. Things like that, right? So you can use these kind of tricks. You have to, now this, the right hand side is now a vector which with many elements. Maybe you have 100 grid points, maybe you have 500 grid points, right? So for each grid point you have to fill this right hand side. You don't, of course you don't want to write pi right hand side of 1 is this and of 2 is that. You have to make a loop. Either you make a loop over the eyes or you just have this with vector operations, right? Okay, what else to say? Yeah, I think these were some of the basic technical points which come up. So now, yeah, question to the audience just to see that we prove Thomas wrong. Who has further questions? What are other things which came up, which you think you need to have explained better? Yeah.
So I have a confusion. So we have a loop over I, which
right.
is the grid point.
Right.
So are we proceeding like, so for each grid point we'll evolve over time and then move to the next?
Right. So this is so for example, this is one of the important things to explain. Right. So now let's just look at that so that that's really clear. What we cannot do. Right, so now we have, so this is x here, this is our x direction, and then this is our discrete space-time. Here we have the time direction, so this would be the next time step here, one time step later, and here we have these same grid points. Just quickly draw our grid points. So the thing that we cannot do is, for example, pick this grid point and then step this grid point to the future. We cannot do this. Why? Well, because of course we have this stencil. So for example, at this point in the future, the information depends on this one and this one and this one because we're coupling to this nearest neighbors, right? So here, if I want to update this one, I also need information from this one and this one. So I have to update the whole solution vector to the next step. And once all our grid points are here, then let's do the next one, right? In principle, for most of you that use a programming language where you just do the whole array together in a vector notation, there's not really much to do because, well, just doing this for the simple, Euler step, right? And it's really something like, y new, right, is y old plus dt times the right-hand side vector. So now this is a vector, this is a vector, this is a vector. There's nothing else to do. If you use, for example, Python, you don't usually have to define the type. There's nothing that you have to change in the code of the Runge-Kutta method. It's just now the initial data are vectors, so the update scheme just adds vectors. Okay, and there's nothing else to do. There's more, for example, problems than which you may have by dealing with vectors now is of course when, for example, you save the solution, you may have to do things slightly differently, or afterwards when you plot the solution, you have to do things a bit differently.
For RK2,
yeah.
for example, the IISc involves f of t plus h by 2. So I need an intermediate data set, right?
Right, exactly.
So do I just approximate it to the earlier one, or how do I do it?
You just do that, and so for RK2 or RK4, right? You have these variables which we called K1, K2, and so on. K1 equals, and again, these are things which now, if the right-hand side is a vector, comes back as a vector. Now these K's are vectors, and in order to compute a new solution, right? There are these formulas like for Runge-Kutta 4, or something like K1 plus 2K2 plus 2K3 plus K4 divided by 6. If I could remember the coefficients correct. Okay, so now all of these things are vectors. And the new updated solution is also a vector.
Now these are seen, there is h by 2, like half times that.
Yeah. A1 plus.
Sorry. Okay, sorry. All right. Now, right, in the formula for the Runge-Kutta integrator, it provides for an explicit dependence on when we compute the right-hand side, right? So when we compute this right-hand side function, which would be the thing that corresponds to the f here, this provides for an explicit dependence on the time and on the state vector. In the case of the wave equation and in any of the partial differential equations that we consider, like the Einstein equations, there is no explicit dependence on time. In the Einstein equation, there's no dependence on time explicitly. So things only depend on the solution vector. And so this part where you have to explicitly update the time step is now necessary, right? What we do have to consider is that it takes, for example, for Runge-Kutta 4, it takes 4 steps. We have to compute these 4 Ks, and we have to evaluate the right-hand side 4 times. And so the logic that's behind this is, if these are our initial, if this is the initial time and the initial data, and this is like 1 time step later, of course we have, what we have actually done, we have also done these like intermediate time steps, which are just hidden in the Runge-Kutta algorithm, right? So it takes several function evaluations and several intermediate time steps to actually get to the final complete Runge-Kutta step. So, for example, if we have some boundary conditions to apply, like periodic boundary conditions, it's not sufficient to just do them here and there. We have to do it for every intermediate step. Okay? Which we can code it up in different ways. We can do, whenever we compute one of these intermediate steps, K1, we apply the boundary condition. Or we can say, when we compute, so here this was our original equation. When we compute this right-hand side, for example, where we have to take 2 derivatives, then at the end points, where we have to get data from the other side, we have to make this computation of the derivative consistent with the boundary conditions. So, for example, we could write a function which takes an input function and computes 2 derivatives, 2 spatial derivatives, but it treats the endpoints differently, and so automatically when computing the derivatives, we take care of the boundary conditions. And then this will be the only place where you have to take care about the boundary conditions. Okay? That would be a very convenient thing where to put in these boundary conditions. Just put them into the place where you compute the derivatives. Right? Because derivatives is where you couple to your neighbors, to your neighboring grid point. That's where the boundary conditions are coming in. And so when you just put this into this feature into the derivative computation, then you have taken care of it. And you have to compute your right-hand side for every full step. You have to compute the right-hand side 4 times. You have to compute the derivatives 4 times. And then the boundary conditions are taken care of every time. Okay? But I think it's an important point. I think it's exactly these things which are a little bit difficult to understand and to sort out in your mind, and how to put these things in the code. Yeah.
So the example you gave for initial Gaussian curve for the wave equation.
Mm-hmm.
The final initial function was the Gaussian a to the minus x square.
Right.
And now the area under the curve.
Mm-hmm.
Will it be conserved as it moves, the wave moves?
So what is going to be the quantity which is conserved? Okay, it is the energy that we talked about, right? So remember when we talked about the Klein-Gordon equation, which of course includes the wave equation, and we talked about existence of the whole thing and so on, and well-posedness. And in this process, we used the definition of the energy. Okay, so we had some energy density. Let's call that rho. We'll talk about it a little bit later again. And so this was gradient squared plus time derivative squared. Now we are in 1 dimension, so this is just phi comma x squared plus phi comma t squared. and the integral of this thing, so integral rho dx, that's the energy, one number at each time, and this is the quantity which is just going to be conserved in time. Okay? So it's not directly, for example, phi, for example, well, we see that in the formula, but the energy depends quadratically on these derivatives, and that's the quantity which we can check to be conserved. But there was another very good question yesterday. Right, was why don't we try to come up with a simpler way of formulating the equations? Okay, well, this was a very, very good question, right? If we look at the wave equation, for example, it looks like we can actually write it in this product form, right? Phi of t and x. It's just some function a of x times some function b of t, for example. Why don't we do that? Okay, we can, right? And in fact, if we do this, we can derive an exact solution, right? We get some kind of eigenvalue problem, and we get an exact solution that this will have the form e to the, well, let's write this now with plane waves, right? So this will have the formula e to the ikx minus omega t, which does have the product form, right? It's e to the ikx times e to the I omega t, right? And so this is just like the fundamental solution, a plane wave for a particular frequency. And in fact, this was one of the main topics that we've talked about before, that if we have these linear constant coefficient systems, we can solve them explicitly as a superposition of these fundamental plane waves. And we use this to understand well-posedness, and we've used this to understand numerical stability. Okay? The point is that while this understanding of the partial differential equations properties is based on essentially the linear constant coefficient case, as is the development of the methods, all this mathematical theory and the methods can also be applied in the same way to more general equations, to nonlinear equations. Okay? Like the Einstein equations, for example, where we cannot rely on the exact solution. So what we're doing right now when we're solving the wave equation, we're solving numerically an equation that we could just write down the exact solution very easily. And you have done that in classes before, right? We know how to do that. But all this theory of what are the properties of this PDE, what numerical methods we can use, while the derivation is based on this simple structure, the methods don't rely on that, and the methods will just work the same way if the equations are nonlinear and in more dimensions and more complicated. Okay, so all we have to do is just understand these very general principles, these very general methods, and we can solve complicated nonlinear equations. The only basic restrictions for the methods that we're learning here is that these equations are quasi-linear, that they're linear in the highest derivatives, and then in all the lower order terms they can be as nonlinear as they want. Okay? So this is very important to keep in mind. So this is the one main restriction. The other big restriction is if your equations are linear, the solution will always exist for all times. Okay? It may grow exponentially, but even if it grows exponentially, it will exist for all times. Right? If there was this simple case of y dot equals lambda y, if y is positive, it's growing exponentially, which many of you have solved it numerically, and you've seen that while the accuracy, of course, is not great, right? If this grows and grows and grows, but the solution exists for all times. We have also seen this other important example, y dot equals lambda y squared, which has a nonlinearity, and in this case, we can't find an exact solution, but in this case, the solution doesn't exist for all times. It becomes singular after a while. So for quasi-linear, but still nonlinear equations, this is kind of the typical thing that we have to expect. Okay? We have a well-posed evolution for some time. We can use the methods which we develop using the tools of linearizations. We can use them to say that this is an okay equation, but after a finite time they may just become singular. Okay? As, for example, is the case for general relativity, because it forms black holes and it forms singularities. And so in many ways it behaves like this equation. Okay? Other comments and questions?
Sir, in this case, is there any restriction over delta x and delta t to get the stable solution?
Sorry, again.
In this method of solving ODEs,
Right.
Is there any restriction over delta x and delta t to get new?
So it's a good question. Is the restriction on delta x and delta t? Now, there can't be. Let's ask about what's the restriction on delta x and delta t. Let's start with the delta x. Okay, is there a restriction that delta x has to have some below a maximum or above a minimum? Okay. Does it make sense that delta x has to be above some minimum? No. Okay. If the algorithm that we use would rely on the fact that delta x cannot be too small, we could not approximate our differential equations as accurately as possible. So that can't be. Okay, and in fact, somehow what all these methods, all this theory that we have developed, what it ensures is that we can take the limit of delta x goes to 0. That we can consistently take this limit and that our solutions are converging in the limit of delta x goes to 0. No. Could it be that delta x is too large? Well, very easily. For example, so I consider your initial data. For example, we said, okay, let's just start with a Gaussian. So here will be our initial Gaussian. So now we have 2, 4, 6, 7 grid points. We can see that with these grid points, our Gaussian is not sampled very well. It's not well resolved. Okay, if we make a picture of a Gaussian with these 7 grid points, we do not recognize it as a Gaussian. Okay, so we cannot expect such an approximation, approximating the derivatives by such few grid points. We cannot expect that to work. So the minimum, what's the actual resolution that you need? You have to find that out by the convergence test. You do the convergence test, and when you get the expected result and you know that your grid spacing is small enough that you can approximate the solution. But you can there's certainly a necessary condition for how small delta x should be, which is easy to say, that if the function has to be recognizable, has to be look nice with the sampling of grid points that you use.
Probably the question is also about how large delta t.
Right, and so now, right. No. So but this is now delta t, right? Now delta t. But this is the story about delta x. Okay. Now delta t. So we have done delta x, right? Now delta t. What we have seen explicitly for ordinary differential equations, we did this simple analysis of y dot equals lambda y with the Euler step, and we have seen that there is a limit that we cannot make delta t too large. Now we have a set of, maybe hundreds of coupled ordinary differential equations, and we cannot expect that the situation is any better. So in general, we do have to expect, of course, that there is a limit on delta t. All right? In fact, afterwards, if you have time, and if not, tomorrow, I will display a general result and some formulas which help us to understand or estimate, at least in simple cases, what is the maximum delta t. For the wave equation, we can compute it explicitly. You tell me wave equation, Runge-Kutta 4, I tell you what's the maximum delta t. Okay? But you can also just come to the same result experimentally with your code. You just run it for different time steps and see what happens. If it looks like a solution of the wave equation, then your delta t is okay, and if it shows rapid exponential growth, very very high frequency noise, you'll see that soon on your own screen, then it's not okay. Then your time step is too large.
Can't we simply use the CFL condition?
Right, exactly. So then this is the other thing that you could use for some intuition. You could use this geometric picture that we had in the talk, right? Comparing the the numerical domain of dependence with the analytical domain of dependence using the speed of light to obtain a necessary condition, necessary but not sufficient for the size of the time step. Okay? So more or less you can't really expect that delta t over delta x is really larger than 1, maybe a little bit larger, but not really much larger than 1, because if it would be that this corresponds to basically the speed of light. This is what defines the continuum light cone, and so by this geometric CFL argument, we can't really expect to make that bigger than that. Okay, we have to think a little bit, of course, because it gets slightly modified, because something like Runge Kutta 2 or Runge Kutta 4 actually has several steps, and that can help us to make this a bit larger than 1. Okay, because actually there are several steps involved, and with several steps means that the spatial stencil is not just 3 points wide, but the number of stages times the fundamental width of the stencil. So we can do this a bit, make our thing wider here, and so we can do a larger step in time. But in any case, it's going to be roughly on that order. Okay.
So the question I asked you yesterday also. Suppose you have different velocity.
Mm-hmm.
Velocity is time dependent, as it knows.
Right.
Now your CFL condition also changes according to that.
Right. Exactly.
So your time. Suppose you want to take the maximum advantage of the computation power. So suppose you take some delta t. Now according to CFL condition, you can change the delta t according to velocity. And now, how can you be sure that this changing of delta t does not affect your energy? Suppose I am computing or calculating something like which conserves energy.
Well, for example, the continuum problem, it will conserve the energy. As soon as we discretize it, it will only approximately conserve the energy. So what we should find is that if we make a convergence test directly on the energy, then the conservation of the energy, that the error that appears in the energy not to be conserved, should go to 0 at the predicted order. Okay? So this is, remember that when we wrote down this convergence test, we wrote this down in a very, very general way, which was a bit confusing, but I think now it shows its value. We wrote that x of h minus x of h over 2 divided by x of h over 2 minus x of h over 4. We looked at this quantity, and x can be anything. And in particular, x can be your solution component. X could be phi, or x could be pi, or x could be the energy or the energy density, or whatever other quantity is interesting to evaluate. And all of them have to converge at the proper predicted order. Okay?
Suppose most of the algorithms we use for integration they don't actually conserve energy, like Euler or RQ4 even.
No, they will not. They will not exactly conserve the energy. Right.
Yeah,
Right.
even
Exactly.
Even if you take leapfrog method, which you showed yesterday,
Right.
which is supposed to conserve the energy, if you take delta t different for different times, then it may not conserve the energy.
Right. But it's, well, we have to live with the fundamental restriction that whenever you compute something numerically, it's just not the exact solution. And so the only way to find out what the properties of the continuum, the true solution, are, is you have to run your code at different resolutions, look at whether you consistently approach the limit, which means you have to carry out the convergence test, and then estimate not determine exactly, but estimate what would be this x0, the continuum solution, and then you can compute an estimate of the error by completely, for example, just computing the difference between this best estimate and the most accurate simulation which you have actually performed, and then it gives you some error bar. And you can, and no quantity which you compute is going to be, more accurate than that. Okay, and so not the solution, not the energy. Everything will have this fundamental error. Okay, it turns out that under certain circumstances, for particular equations, taking care of the particular properties of that equation, you can do a bit better. Okay, so an example which I think I mentioned was that if you have Hamiltonian equations for some particle system, you can actually construct methods which preserve the energy. But then you really take care of the special properties of that equation. If you have a very complicated nonlinear system of equations, like, for example, the Einstein equations, or other complicated equations in physics, in general you can't do this. Okay, so then in general, everything will come with some numerical error, and whether you want 3 digits, or 5 digits, or 12 digits, you have to have some extra information. You have to know, do you want to compare this with the experiment, and more than 3 digits makes no sense, or you want to give some information to mathematicians which really they want to prove some theorem, and this is a very subtle effect, and you really need actually 12 digits to make your point. This is this extra information. There's a fundamental number which comes with your hardware, which is this double precision, which is about 16 digits. Right? That's how accurate any floating point operation is usually on your computer. But it's just something from the hardware. It's a convenient number because for most practical purposes, that's much smaller than what you need. But it's just if you do a very complicated situation calculation with many grid points in many time steps, and somehow then of course your total error picks up this 10 to the minus 16 error everywhere for each operation that you do, and then maybe if you actually compute your error, and let's say you do 10 to the 4 operations, then maybe the error that you actually find cannot be better than 10 to the minus 12, because 4 digits you have spent on how many operations you do, right? If you say, for my purposes, I need an accuracy of 10 to the minus 7, and my fundamental limit that's given here is 10 to the minus 12, you're fine, right? There's absolutely no particular motivation to go down all the way and make it as accurate as the hardware provides you, because it makes it more expensive. Somebody has to pay for that. Whatever the simulations that we do, they're very often, if you do go to 3D, they're very expensive. This costs a lot of money whenever you press return. Maybe it's a lot of money in electricity, and you should not compute things more accurately than what you need. You shouldn't compute it less accurately, but yeah.
Possibly I should have asked it previously. The measure of convergence that we are testing with this formula, you told that it should limit to 2 power n.
Right. It should be approximately that. Yeah. Right.
Yes. Now, if I'm having, if in my calculation, I have already reached the limit of convergence. Let us say all my values at any resolution, the value is same.
Right. Okay.
That means it's maximum converge, but it is 0 by 0. What I want to know is whether it is better than, it is lesser than 2 power n or greater than 2 power n. What is a better? From which direction?
No, you mean if you none of the two is better. Okay, you have to this convergence thing right here again. So you can say, well, this is something like 2 to the n, and I'm interested in what is this n. Okay. you have a prediction what is consistent with the algorithm that you think you have implemented. Okay? So let's say you find, let's say your prediction is runge equal to 2, which means you think this should be 2. Now you find 3. That means that maybe you just made a mistake and the algorithm that you coded up, this is not the one that you thought you coded up, and we have to track that down. Or just the resolution isn't good enough. So you have to refine the resolution. If by refining the resolution you approach this number, let's say we discussed it before, you start with 3, you do 3 resolutions, you get 3. We don't know what happens. You do another smaller 3 resolutions, you get 2.5. Well, that's certainly promising, right? You do it further, and you get, whatever, 2.1. More promising. You go even further, and you get 2.02. I would say at this point, it's perfectly consistent, and spending any more computer or human time on the convergence test is pointless. If it turns out that the error that you compute is not yet good enough, because you want it, because some experimenter, he actually needs it with 8 digits. Surprise, surprise. Well, continue. Refine further until you have the accuracy that you need. But for the purpose of convergence test, you're okay. Whether, if this number is, you want 2, whether this is, you start out with 3 or with 1/2, it doesn't really make a difference. Because the goal is you have to get close to 2. Okay?
What I want to tell is...
Like 3, like you say, convergence order of 3 looks better because it's converging faster. But the information that you have is if you see 3, you don't know what's going on. And if you see 1/2, you don't know what's going on. So practical information is exactly the same.
He has because whether you can get this expected than in a more faster convergence than expected because your resolution is too high, not too low.
If no. So as the better the resolution becomes, right? Let's just write this formula down again here. Asymptotically, your error should go like x of h, which means result as a independence of resolution is going to be something like x0, the continuum result, plus some coefficient, I call it e for error, times delta x to some power of n, say, plus order of higher orders. Let's write higher orders as delta x to the n plus 1, right? So this means that if your delta x is small enough, you have this approximation, your delta x can't be too small for that. Unless your delta x is so small that the error becomes on this order of 10 to the minus 16, where your numbers are too coarse to be precise. So for example, we had, I think with you, right? We had that yesterday. So you computed the this convergence order n for the case where we had this decaying ODE, and for some time it looked perfectly 4, and then suddenly it gets very noisy, right? So let's draw this curve, right? We plotted n of t, and here here's 4, and it looked like, actually there was some initial transient, and we can talk about it maybe separately, and then it like perfectly 4, and then suddenly it looked like that. Okay, what does this mean? Well, if you plot the actual solution, the solution would go like this, this exponential, actually stronger than that. And that's what this exponential solution looks like. So here, there's just no solution left. And so the difference is, x is very small, the difference is very, very small. If you divide a very small number by another very small number, it's very inaccurate. And so then it just looks like that. But it's nothing bad. It means that your solution is already so accurate that the error is just not well described by your finite machine accuracy. So just switch off at that point. Okay? Quite often, and somehow this can easily happen. It may well happen with your solutions of the wave equation. If your you implement consistent fourth order accuracy, you use 500 grid points, you may easily, just for these simple profiles of a Gaussian or what we do next week with black holes and so on, you may easily hit round off actually. And then you will see this again. Things come a bit noisy because the numbers, the machine numbers are not accurate enough. All right? Okay, so now we spent a lot more time than I wanted, but this means that my slides are sufficient. Haha. Always have to think ahead. So do you have a general belief that we can all sort out the wave equation until tomorrow or so? Optimistic?
Yes.
Oh, very good. I'm also very optimistic. I'm less optimistic I can get my own Python code to work, but you can certainly do it. Many of the things that I wanted to say in a lecture, so then I can move on super fast. Let's review the lab goals for today. Many of the things that we just talked about. So you will eventually code up the wave equation, and today or tomorrow you also look at further quantities like the energy. How well is the energy conserved? And then this other thing, look at these characteristic variables, right? What we talked about today is that the characteristic variables are some linear combinations of your variables which just move with a well-defined speed in one direction, to the left or to the right. Compute these variables in the code and see whether that's what they're doing. All of you, eventually, you should upgrade your code to fourth order centered finite differences. Start with the second order, which I gave you the equations, and then I'll just display later in the lab session today or tomorrow. I'll just display or hand out the formulas for the fourth order. I'll talk about boundary conditions later today or in the lab session, so you should also implement this. And then I told this to some of the people who asked me yesterday, right? We learned about the Euler, the Runge-Kutta 2 and the Runge-Kutta 4 method for the integration. So it turns out that Euler and Runge-Kutta 2, they do work just fine for ODEs, okay? But they do not work fine for this method of lines. So when we have this partial differential equation situation where we want to take the limit to infinitely many coupled ODEs as delta x go to 0, it turns out that these are not stable. Code them up, try it out, and see that it doesn't work, okay? So in other words, for these you cannot make delta t so small that it works, okay? So it doesn't. I'll talk about the shifted wave equation today because I think it's quite interesting as a very simple case of the wave equation, which helps us a bit better to understand what happens in the Einstein equations. If you have time, implement it. If not, I think it's you can do it whenever you feel the need to it, when you become a professional numerical relativist. And then I'll give you the coupled Einstein equations, so a scalar field coupled to the Einstein equations. Again, now we're in the lab session. You'll see the equation. We can start, as you implement your method of lines, you can start to plan ahead what you have to do to implement these equations, okay? Now, there's another thing which I want to say, and the whole next week that David is talking to you, he will devote it to this topic. What I'm telling you about these simple methods of solving PDEs, they work well if you have smooth solutions, okay? But it turns out in physics it's also quite common that you have non-smooth, that you have distributional solutions. And this happens in particular, so if you have a fundamental field, like the metric for the Einstein equations or the scalar field, then usually because you have nice, well-defined equations, the solutions are going to be smooth. But if you have something which is phenomenological, which doesn't have a well-defined physical limit as you go to small scales, like a fluid, for example, right? A fluid makes no physical sense at small scales, because at small scales it's just not a fluid, it's atoms and molecules. It's different, okay? And so this creates funny features and in particular distributional solutions which require entirely different methods. They're based on what we learned this week, but they have other features, and that's why a whole week lecture series is devoted to them. A typical example is this Burger's equation. You see that here what happens is that this ut is ux, so the characteristic speed depends on the solution. And then you can have funny features like this one here. This is a wave. You start with a Gaussian at time equals 0, but the Gaussian kind of tips over like a wave that's breaking. And that's a singular solution which we cannot treat with the methods that we're learning here. So I wanted to display this slide, and I've said most of the things in my monologue before, but we want to approximate the solution to a PDE with an error estimate at some affordable cost, which means not just in running the code, but also in developing the code, in modifying the code to treat new problems, okay? And so we only need a certain accuracy. It may not be easy to understand what that accuracy should be exactly. For example, for this problem of gravitational wave simulations that many of us are interested in, it has been a long-standing and not entirely completely resolved problem. What's the actual accuracy that you need for your observation? Yeah?
In the previous slide where you showed the graph for the Burger equation,
Right.
the solution is like not very physical because it's like one of the soft conditions where
Sorry?
the solution is multi-valued.
Right, but it is multivariate, right, exactly, yeah, right.
So I think like there we add like artificial viscosity term.
So David is going to tell you all about it. He's going to tell you all about artificial viscosity and how you can do better with other methods. Okay, but he will a whole week on that. Right. So you don't have to do things more accurately than what you need. But also, I would say what's very important is don't waste too much time trying to interpret poor numerical data, which have a lot of noise and a lot of garbage. You can waste a lot of time doing this. Just use that time to produce better data. It sometimes is a good advice. And don't become obsessed with some machine accuracy. Accuracy it has to serve a purpose, whatever you need. Okay. All right, this is another comment which I want to make, right? So computations can be very, very expensive. And I think, if you have a good idea about a good problem, an interesting physical idea, and you have a code which works fine, computer time is quite likely to come to you, okay? The important thing is really you have the ideas, you have a code which works. All right. You have to be very careful with planning your code, because what you will see is that most likely the main amount of time that you spend is actually debugging your code, or just trying to figure out what's going on when the data are actually poor. So try to minimize the time and try to maximize the time that you can do with physics, having new ideas, new papers, with good quality data. There's this keyword, one keyword which I think is good advice I've heard. It was like defensive programming, right? Defensive programming is like defensive driving. Just anticipate what other people may do. I don't see a lot of accidents on the street. So my feeling is that in India, they actually do practice defensive driving, okay? Just assume that other people on the road may do strange things. Okay? You all can relate to this, I think. And so do the same when you write a program, okay? All right, you can look at this in your slides, right? I have a whole program on defensive programming. Keep it simple, as simple as possible, okay? Now, yesterday we derived explicitly the finite difference stencil, the finite difference formula for the second order accurate case using an interpolating polynomial. And sometimes, because we're working a lot in the Fourier domain, it's actually useful to also translate these stencils to the Fourier domain. Okay, and I'll show you how this works. So yesterday we derived these formulas for the first and second derivative to second order accuracy. And then if we want to translate this to the Fourier domain, we can just say, okay, what happens now if the function that we want to differentiate is something like a sine wave, e to the I omega x, okay? And now we have this function, we apply this algorithm to that function, and for example, for this one, we just get e to the I h omega minus e to the minus I h omega over 2h. We can simplify this, and we just see that now in Fourier space, the finite difference operator has become I times the sinus divided by h. Okay? And this makes a lot of sense because in the continuum, what's the derivative operation in the Fourier space in the continuum? Of course, it's just multiplication with I omega. Okay? And in the discrete case, we have I sinus h omega over h, which we see that for small frequencies is the same as in the continuum. But for larger frequencies, it deviates. If we have a signal in the Fourier domain at larger frequencies, means we don't have enough resolution. We have some very, very high frequency waves which are not well resolved, and for those, the difference operator is not accurate because sinus deviates from just h omega. Is that point clear? We want to make this especially clear for the data analysis people because it's it's useful for you to understand that the Fourier domain plays such an important role.
So I was taking outside, so I missed your last statement.
So it's you're here, right? So in the continuum it's just I omega, but in the discrete case with some discretization delta x, which we call h, it becomes this formula which we have derived. And then for small omega, it's got the same as in the continuum. So for small frequencies where the solution looks smooth, we have a good approximation because sinus is the same as the continuum. But for high frequencies where the solution is not well resolved, then we have a significant error. And we see this nicely in the Fourier domain. Okay. And here, you look at this formula, you don't see exactly what happens, but in the Fourier domain, you see this very nicely. Okay, so now that we are able to do finite differencing in the Fourier domain, we can do a full analysis in the Fourier domain, and this analysis is the same or completely analogous to the analysis which we did the other day in the continuum. Just understand what did we do? We constructed the explicit solution in the continuum. Then we computed the norm so that the norm was preserved. And then we could conclude things are well posed. And we saw that the cases where this is true are the strongly hyperbolic systems, and these are the good cases of partial differential equations. So let's do the same in the discrete case. Let's start with some differential equation. We consider the case where it's linear and constant coefficients. So u dot, where u may now be some vector, can have several components. There will be some function of the derivative x, so there's some derivative operator. Maybe so p could be just dx, or p could just be dx plus lambda, which also includes a source term, for example, right? Or p could be 3dx plus 5 lambda, whatever. And we apply this derivative operator to our solution here. Then we can Fourier transform that, and we call that p hat, Fourier transform. And so then d by dx is going to be replaced by I times omega. And we saw that there are two kind of normalizations which are useful. We can write it like this, or we can introduce this psi, which is normalized with a different factor of h. If you want to compare this with the formula, the equations which we wrote down for systems of partial differential equations, right? This thing here there was a matrix A, right? And so now in this case we'd have p hat would be I omega A, because it's like derivative times the matrix A. And then we saw, or I tried to say that we claim that well-posedness is equivalent to an estimate in the norm. So we have to, now we can construct the exact solution, and we have to say that e to the operator times the time has to be less than, sorry, I forgot the initial solution here, I apologize, then these constants times the initial solution. And we saw that in order to have that, we need the principal part diagonalizable. Right? Now, since this was diagonalizability of this matrix A, just multiplying this by omega doesn't change anything. Right? So it's all about whether the matrix can be diagonalized or not. So this was for the continuum, but now we want to discretize that. So discretize it, for example, to second order centered accuracy, which means that we just apply the formula which we derived before. We replace d by dx by I divided by h times sinus psi, so the sinus of this frequency, normalized frequency, exercise, we just did the exercise in the previous sheet. And now, after we have discretized, we can do our method of lines Runge-Kutta, which we talked about before. We can write the solution at the next time step times some operator q times the solution at the previous time step. What is this operator q? It's just what comes out of the Runge-Kutta algorithm. The Runge-Kutta algorithm approximates the exponential function to some order. So this just means that this thing is really just the exponential function of its argument cut off at some order, right? Do I have to, what was the time? What? Half an hour more, right? Since my watch broke down, I'm completely... Okay. Where are we? Okay, so we just insert this, and we can, so now we can write the whole thing in the Fourier domain, right? So just putting hats and psi's as the arguments. Then we can just solve this, and we can write explicitly the solution at time step n in terms of this operator and the solution at time step 0, so the initial data. And since so this is this what we called before the amplification matrix, right? The thing which takes us from one time step to the next time step. We have n time steps, we take this to the nth power. And this is diagonalizable if we have the fundamental differential operator diagonalizable. And we have stability if the eigenvalues of this are all bounded by 1. Okay, it's the same way that we've had that before. So this means that if the original operator is diagonalizable, which means that if the A is diagonalizable, this all works out. We get a diagonalizable discrete update operator. We have it stable if the eigenvalues are bounded, but since the eigenvalues also depend on the time step, we can also always make it stable, make the eigenvalues small enough, but just making the time step small enough. And then there is a very useful general result, which is, this outline here is just that you have seen this once, and if you want to understand it better, if you look in some textbooks, then you can look at this in much more detail. But the one thing that is important to remember is that what you can show is that you have the following rule for the time step, unless, of course, so this is unless the PDE depends explicitly on which direction it is. Okay, but if it doesn't, then this time step ratio delta t by delta x is something which is essentially given by some number alpha 0, which is 2 for some integrator which I haven't talked about, square root of 3 for the third order Runge-Kutta, and square root of 8 for Runge-Kutta 4. Okay? Why didn't we list Runge-Kutta 2 and the Euler method? Sorry?
Why is the restriction on delta t and delta x?
Why is it?
Why do you have the dependence on delta t and delta x?
Well, we have this fundamental dependence, right? Because just remember, right? We expect that we have such a dependence because we already had it for ODEs. And now we have this dependence because the eigenvalues of the update operator, they have to be smaller than 1. And in order to achieve this, we can do this for any right-hand side function by just making delta t smaller. So we have this kind of restriction. Okay? And so Sorry, so we don't list here Euler and Runge-Kutta 2, because for Euler and Runge-Kutta 2, as we said before, you cannot make delta t as small that this works. It just that never work. Okay. And then you have two more factors. It's the spectral radius of your original operator. So something which depends on the eigenvalues of this matrix A, which maybe in practice means easy to compute for the wave equation, very complicated for the Einstein equations. Okay. And then there's a factor which is the square root of the dimension, the spatial dimension. So if you want to run a code in 3 space-time dimensions, then the maximum time step goes. You have done your Einstein equations in 1 dimension. You found a certain maximum time step. In 3 dimensions, it's square root of 3 smaller. Okay. So going to higher dimension is expensive for many reasons, and one of them is this. Basically, everything that we've said so far, we always used linearity, but we really want to solve nonlinear equations, right? If you wouldn't want, otherwise we don't have to do any numerics, because for the linear equations we just wrote down the explicit solution, and that's what all the maths that we developed is based on these explicit solutions. So how do we actually deal with nonlinear, means quasi-linear partial differential equations? It turns out that what happens for those is that because of the nonlinear interactions, you can get a coupling between the low frequencies and the high frequencies. You can transfer energy between them. You can, in particular, you can transfer energy from the low frequencies to the high frequencies, which are not well resolved, which means your error grows a lot, and you can become unstable. What we have to do to deal with this problem, we have to damp out the high frequencies, right? In the high frequencies, there is no physical signal, right? Is that this is a key point. We all agree on that, right? You take a nice function, which is your initial data or some snapshot, right? Some smooth function. My functions are never very smooth. And do the Fourier transform. It's because a smooth function, the Fourier transform drops down exponentially. So you have no power in the high frequencies, right? These high frequencies are the ones that are badly resolved. So if you set your high frequencies to 0, it doesn't change anything, okay? And because you can just, by nonlinear coupling, you can transfer energy to these high frequencies and just blow them up. Right? But what happens if you put somehow more energy into the high frequencies of this function? Right? We Fourier transform, add some funny garbage at high frequencies to the Fourier transform back. Well, it's just high frequency features here. Right? But they have nothing to do with the physics. Okay? So what we have to do, well, we just have to add some low pass filter. If you work with the Fourier transform, you can take the Fourier transform, look at the upper third of the frequencies and just set them to 0. If you work with a finite difference method, there's something else we can do. We add dissipation the following way. To the right-hand side, we just add another term, which in general, it has this form. Okay? Strange form, where does it come from? This is, there's one bad thing which I've done. I have not defined these things. What is D plus? D plus is just u of I plus 1 minus u of I divided by delta x. This is just the fundamental difference operator, first order accurate. D minus the other thing. Okay. So this is some derivatives to the power of r times delta x to some other power of r with some extra normalization factor. Okay. At the lowest order, so for example, when r is equal to 1.
So are some sort of parameter that you put in, or
sorry?
What is r?
I'll explain it now. R is the order to which we want to do that, but I'll explain this now. So let's look at r equals 1. Okay? If r equals to 1, then we have d plus d minus, so this is like the second derivative. Let's write the second derivative as Laplace. Let's just jump to higher dimension Laplace operator. And then here we have, so if r equals to 1, then we have 2 minus 1 is 1, so we have minus delta x. Right. So what we are doing, I'm confused about two.
What is d minus? Difference over in the other direction. D minus is
It's just a difference in the other direction. Exactly right. So basically, what we're doing here is just adding a term with a Laplace operator. What does that mean? Adding so this more. If we just have this equation, u dot equals Laplace u, that's the heat equation. It damps things out. Right? So if you just add such a term to a right-hand side of a partial differential equation, it creates some damping effect. It just damps out the high frequencies and gets this thing away. Okay?
what's the relation of this? Where does the sort of frequency come in here?
Well, here, because the finite difference world doesn't really live in the Fourier space, so we cannot just say, well, we could Fourier transform and then operate this way, but it's extra cost. So we just want something which modifies the equations in such a way as to have this kind of damping effect, as would have the heat equation. So what we do is just we add a heat equation term to our evolution equation, just a small one, to just damp things out.
So how do you make sure that this doesn't damp out the high frequencies that we are interested in?
So there are two things. Okay, one thing is we actually multiply this now with delta x because the delta x survived, which just makes this actually converge away for high resolutions. Right? Because this goes to 0. So in the limit toward high resolution, where everything becomes well resolved, the damping effect goes away. Okay? And if we want, if we make r higher than 1, then then this is a higher power analog of the Laplace operator. It vanishes with a faster power of x, and is chosen in such a way that at Kreis-Oligger dissipation, this is the name, Kreis-Oligger dissipation, for a 2r minus 2 accurate scheme. So let's say if r is equal to 1, we have actually 2 minus 2 is 0, so that doesn't work. We have to use at least r equals 2, then we have 4 minus 2 is 2. For a second order scheme, we have to take this formula with r is equal to 1. Sorry, r equals to 2, okay? So the higher the order that you want, you have to choose a different r, and then you have to change the normalization factor in this way. Why? Because you can just prove a theorem that this has indeed it has the desired damping effect that we want to achieve. For r equals 1, this is kind of intuitive in the way that I explained, and you can just prove that in general this just works as.
This is irrespective of the real frequencies in your system.
Well, if your solution is very poorly resolved, then this will have a strong damping effect, but just because you're poorly resolved. Okay, so you can only expect that everything together behaves nicely in the limit of delta x becomes small, which you have to find. What value of resolution you need? Well, you have to find by the convergence test. So this is one subtlety, but there's another subtlety, which is what happens if this amplitude, there's a parameter, a number, sigma. If we make it large, we say, damp it out as much as possible, right? I still have some noise, just make this larger. Well, we know that, so this is like adding here a sigma. We've briefly mentioned this before, that the heat equation, the parabolic equations, they have a much more restrictive time step. So if this thing goes up in amplitude, your time step goes down. So you cannot just damp as much as possible, because at some point you just hit the CFL limit, and you have to either make the time step smaller or you have to make this smaller. Okay, you cannot have a hyperbolic equation and make it look as much as a heat equation as you want, because it just behaves differently. Okay? So the usual thing is you cannot, there's not a lot of risk to damp out too much, because if the amplitude becomes too large, it just behaves too much as a heat equation, and the time step becomes very small. So this, yeah. Unless your solution is supposed to have very sharp features, right? That's this distributional case. Then adding this artificial dissipation can cause you trouble, because it's supposed to have sharp features. You cannot just, they're physical, right? You cannot stamp them out. Okay, so this is something that we can always do. For example, the wave equation, it is linear constant coefficient, so we don't really need dissipation. But if you go to the Einstein equations, nonlinear, then in general you do have to do this. You do. Yeah, basically, as soon as it's nonlinear, in general, that's what you have to do. So we said all of those things, and there is one topic which I think I'll just skip that absolutely completely, but I want to have it mentioned. I will skip the technical part. You will see it on the slides, but I want to at least mention that. We have developed this theory of first order hyperbolic systems, and then we identify the good ones, which are, we call them strongly hyperbolic. But you're seeing in Thomas' lectures that the Einstein equations, they don't look quite like this, because they're second order, and so they are second order in space. So what do we do with them? Okay. Well, one thing that we could do is we could just do a first order reduction, just as for the wave equation, and introduce more variables and convert everything to first order. Okay. Problem is that you have seen this for the wave equation. We defined a new variable which was called psi. Psi is defined as phi comma x, but then during the evolution you have to check that that's still satisfied. So you have enlarged your phase space by more variables, but then you have to make sure that these artificial relations here are actually satisfied. Now, if you have nonlinear equations which can go quite bad, so unphysically enlarging your phase space by even more variables is not necessarily a good idea, because these can be unstable. But and so this can create extra instabilities that were not there in the physical system. So it would make a lot of sense to not do this operation, not work with not hammer everything down to first order in space systems, but just stay with the second order in space things. Just with the idea of just keep things simple, and so directly use the kind of systems that Thomas is going to talk about: ADM, harmonic, BSSN, and so on. Because they just don't fall into the standard form, it took quite a while to figure out the mathematical theory for them, and to find out that you can also develop an understanding of well-posedness for these systems, looking at them directly, but it actually took until about 2004. It really took a long time to understand the mathematical properties of, for example, ADM and similar systems which we use. Okay, and if you look at older literature, this can give rise to a lot of confusion. Okay, but now this is quite reasonably clear. But I just want to, here I have worked out, for example, a few things about treating the wave equation as mixed order, and showing that by looking at the Fourier space, that there's nothing wrong with writing the wave equation as mixed order, second derivatives in space. Okay, and I just include this here, and I give these comments just to, if you really want to go more into the literature and just understand what's happening, or you code up the Einstein equations, to have an understanding of what's actually happening here. All right. There's another thing which I just want to briefly mention is we have now, so we talked about, for example, the energy as somehow as a derived quantity, and we also want to show convergence for this derived quantity. There are other quantities which are interesting. For example, there's the propagation speed of the waves, right? You know about wave phenomena. You can have the phase velocity of a wave, you can have the group velocity of a wave. If we only have the physical speeds, these velocities should basically be the speed of light. But if we have a numerical scheme, we cannot expect that a numerical wave propagates with exactly the right velocity, right? If the wave is accurately represented, which means it has like a low frequency, this is going to work well. But if the frequency is very high, if the grid is too coarse, your numerical wave is not going to propagate at the right speed. Okay? And so the quantities to characterize this are, again, the phase velocity and the group velocity in the numerical setup. How do we compute them? Well, jumping a few details, right? The propagation velocities, they were the eigenvalues of this matrix A, right? We had to remember that, just let's write it down again. We're always thinking of a system in the form, right, U dot, this is a matrix, this is A time A dx U, something like this, right? And this is a matrix. The diagonal form of this matrix tells us about the eigenvalues tell us about the speeds, the different speeds of the different components. And doing this on the numerical level, we don't take the matrix A, but we take this numerical principal part, which we defined previously. We compute the eigenvalues, and then phase velocity is just eigenvalue by frequency, and the group velocity is d lambda by the omega, right? Why do we have an I here? Well, it's just because we had an I in the convention of this thing here, just because it's a general convention, okay, just for simplicity. So in your numerical scheme now, for example, you could compute what are the phase velocities and the group velocities as a function of frequency for different schemes, okay? And we have these plots here. For example, here we have this so phase speed and group speed. For what? Red is the advection equation, green is the wave equation, second order, fourth order schemes. So second order in space, fourth order in space, evolved with Runge quota 4. And so we see, so here this is the oops. This is the frequency 0, and here are like the small frequencies. Here's everything that's well resolved. What was the maximum frequency in the grid? It was plus pi, and for every positive frequency there's a negative one, so plus pi, minus pi. All these things, of course, they are symmetric, right? And so what we see is that, for example, we have a second order would be this one, wave equation. This is second order, this is fourth order, right? So we see that the fourth order, the more accurate scheme, right, extends the exact value of propagation, which is 1, to larger frequencies. It's more accurate, okay? And then for very high frequencies, the error in the propagation speed becomes large. For the advection equation, curiously enough, and this means that basically whether we discretize first order in space, second order in space, for the advection equation, the curve looks quite different. This is worse. But we all know that more important than phase speed is group speed. When we look at the group speed, that's even more interesting because so here it's 0. You don't see it very well. Here this is 0. Here's plus 1, the correct value. Here's minus 1. And we see that for the wave equation, we always get the correct sign of the speed. For the advection equation, at higher frequencies, the sign actually changes. Right? If you would evolve an equation with a black hole, where you know physically that no information can come out of the black hole, what we see in this analysis is that for the advection equation at high frequencies, the waves just go the wrong direction. So they would, instead of going into the black hole, they come out of the black hole, which is probably not a good thing to have. Okay? What would we do to counter that? Well, because it happens at these high frequencies, just add more dissipation. Because to kill the modes which come out of the black hole. Okay, so very, very, very important. All right, now in the last 25 seconds, let's look at some simple incarnations of the scalar wave equation. We can define that with a metric. So now, if you just do this, right, this is minimal coupling. Now we have written metric covariant derivatives. Now we went from our ordinary wave equation to the wave equation on some curved background. And if this metric satisfies the Einstein equations with the energy momentum tensor of the wave equation on the right-hand side, now we have a coupled system, right? Well, the simplest case is, of course, on Minkowski space. Then we're back to the simplest setting. And then we can get 1 plus 1 dimensional problems, which means problems we can deal here in class, either by somehow considering plane waves. Plane wave means that just our function, phi is a function of x and t. And then we have the ordinary wave equation that we're dealing with. Or, more interesting, we could look at spherically symmetric waves, and phi is a function of r and t. Then, of course, we get a different Laplace operator. We just get phi r plus 2 over r phi r, which is more interesting physically. It does have a little problem that we'll have to face, that 2 over r is singular at the origin, and singular is a problem for the computer, so we have to think about how we deal with that. It turns out that for the very simple case, there's a miracle which appears, a very interesting miracle. If we define a new variable, I call it phi tilde, which is just r phi, and insert that, then I get phi tilde tt is phi tilde rr, and it's just the wave equation, the simple one we had before. Okay? So this means that if you solve your method of lines for the wave equation, actually, you can interpret the solution as plane wave solutions or spherically symmetric waves, which are like spherically symmetric outgoing radiation. And then this is the thing this is the problem that we want to invest some more time on. So I think that where Thomas explained that in spherical symmetry, there's the Birkhoff theorem. We do not have gravitational waves, but if you do capture the scalar wave equation to the metric in spherical symmetry, we still have some kind of wavy field which propagates outward at the speed of light. So many of the phenomena which will happen if you have gravitational waves, we can see it in this simple spherically symmetric system. We can, form black holes, they radiate away some radiation, which is not gravitational waves, it's scalar waves. But a lot of the physics that's going on can be learned in the simple case. So let me just stop here, and then for the afternoon session, so we'll continue with our work, we'll continue with the lab, and I'll probably just show a few more slides, like about the fourth order difference operators, maybe some other thing that I come up with, or things that I couldn't say now. Thanks.
I have two announcements before we discuss for lunch. As you have seen, we have no lectures over the weekend, and we will not